Higher Notes Unit 2, Section 6, Refraction. Well, interesting things happen when light travels from one medium into another. So I'm going to draw a block of glass like that. Happens to be square. The squareness isn't crucial. So let's imagine we have a beam of light, and I'm just going to have the light travel straight through the glass block from the air. So there's no change of direction at this point, and that's deliberate so that we can focus on some other things. So first of all, the medium that the light is traveling through initially is air, but it then moves in to glass. And then on the other side, it moves back into the air again. And it's lying right on the normal, i.e. it's hitting the boundary at 90 degrees, so there's no change of direction here. Now, as you'll see in this section, numbering the media is quite important, so I'm going to call air medium number 1, because that's the medium the light is travelling through first, and glass will be medium number 2, because that's the second medium that I'm talking about. So I'm really interested in the transition of the light from the air into the glass. I'm focusing on the first boundary, medium 1 and medium 2. Well, if you were to have a kind of bird's eye view of your light wave and you could see the crests, then you would find that they would look like this. So maybe something like that. So these are crests viewed from above. And of course they should all be equally spaced, because the separation of those crests, of course, is the wavelength of the light. So I'll call that lambda 1, the wavelength of the light in medium 1, which is air. Now, interestingly, what happens to the light once it gets into the glass is that the wavelength changes. It actually gets smaller inside the glass. So we get something like this happening. The crests are much closer together. And that carries on all the way across. Now, I'm not going to complete the diagram all the way across, just for convenience, but you can see that what we've now got is a much smaller wavelength 2. That's the shorter wavelength in the glass. Now, that happens because the glass is what's called a more optically dense medium. And the reduction in wavelength is one of the effects of passing from what's called a rare medium, not very optically dense, into a more optically dense medium. Now, something else that happens, which is interesting, is that when you're in the air, we'll call it V1, well, that's going to be approximately 3 times 10 to the 8 meters per second, the speed of light in air, or in a vacuum. But when you get into the glass, that actually comes down to approximately 2 times 10 to the 8 meters per second. So there's a reduction in speed in the more optically dense medium. And then it returns to the 3 times 10 to the 8 when you come back out into the air again. And similarly, the wavelength goes back up when you come out into the air at 2. So we've got these two features, two changes in the properties of the light as it passes from air into glass. So refraction then is defined as the change in speed of a wave as it passes from one medium into another. Now, where you see speed, you could replace that with wavelength. Could be the change of wavelength, which goes along with the change in speed. This applies to all waves, not just light waves, although we'll tend in this section to concentrate on light waves. You'll notice there's no change in direction of the light beam above, the blue light beam. It's just passing straight through. That's because its angle of incidence is 0 degrees to the normal. It's lying right on the normal. But in most cases, light actually comes in to the boundary between the medium, one medium and the next, at an angle. So let's now consider that more common situation. Let's make this different colour. So let's imagine that we have air on this side and glass on the other side. So that's medium 1 and medium 2. Well, I'm going to bring my light ray in at an angle, so I'm going to draw a normal. As you know, a normal is an imaginary line. It's a construction line drawn at right angles to the boundary. So let's take our ray of light coming in. We're just imagining this is monochromatic light at the moment. It's got a particular wavelength. There it is. Well, we define the angle of incidence, which I'm going to call theta 1, as the angle between the ray and the normal in medium 1. So theta 1 corresponds to the angle of incidence in medium 1. Now the straight through position would be that, but of course, as you will know, the ray bends down towards the normal and going into the denser medium. Does something like that. So you've clearly got a change of direction there. And then we call this angle, the angle of refraction, theta 2. So when you go from a rare medium into a dense medium, the ray will always bend down towards the normal as shown, and theta 2 will therefore always be smaller than theta 1. Now, if you do an experiment involving a ray box, a glass block, and you measure the angles, theta 1 and theta 2, and if you then plot a graph, not of theta 1 against theta 2, but of sine theta 1 against sine theta 2, you'll get a linear relationship. If you plot just theta 1 against theta 2, you get a curved line. But if we go for the sines, it's linear. So let's imagine then we've got our origin there. We've got the sine of theta 1 here. Theta 1, remember, is the angle of incidence. And if we plot the sine of theta 2 there, well, when we plot that, we get a nice direct proportion relationship, which is the kind of relationship we like working with. It's basically a straight line, and mathematically it's easier to work with straight lines than curves. So that's how theta 1 and theta 2 are related. Now if medium 1 is air, as it is in our case, then it turns out that the gradient of that line equals a constant, obviously, and that constant is the refractive index of the glass. Now, refractive index is given the symbol n, so I'm now going to go back and put that in. So this would have refractive index n1, and this would have refractive index n2. And refractive index is effectively a measure of how much refraction occurs when the wave enters that medium. So the bigger the refractive index of the glass, the more closely the ray bends down towards the normal. Now, there's a law which expresses the relationship between the refractive index and the sine thetas, and indeed the speed of the waves in the various media and the wavelength, and it's called Snell's law. So I'm going to give you the extended form of Snell's law, and it says that if you take the refractive index of the second medium, in this case the glass, and you divide it by the refractive index of the first medium, then that expression n2 over n1 will equal sine theta 1 divided by sine theta 2. Now that sine theta 1 over sine theta 2 is basically the gradient of the line. Now you'll see I've got n2 over n1 there, and you're maybe wondering where the n1 has gone in my gradient. That is often omitted because for air, n1 is generally taken as 1, and so you can effectively miss it out. Strictly it should be there, and just be aware that if you're ever dealing with two media where air isn't involved, you need that full n2 over n1 version of the equation. Now it turns out then that this also equals v1 over v2, the ratio of the velocities, and it also equals lambda 1 over lambda 2. So notice the 1s are always on the top of the equation except for the n. So it's n2 over n1 equals sine theta 1 over sine theta 2, which equals v1 over v2, which equals lambda 1 over lambda 2. And that is the extended full version of Snell's law. Let's do an example. So let's imagine we have a block of glass like that. Put in our normal. And let's say that the beam of light comes in like so, and let that be 30 degrees, and the ray will be refracted down towards the normal. I'm not going to investigate what happens at the next boundary, just focus on these two. So let's imagine that's 54 degrees, and the question is, find the refractive index of the glass block below. This is the air, and this is the glass. So that's going to be medium 1, and that's going to be medium 2. Always very important to order your media. Whichever one you're in first is medium 1, and whichever one you're in second is medium 2. Right, solution. Well, the first thing you need to spot here, and it's a trap which many people fall into, is that the angles shown are between the rays and the boundary, not between the rays and the normal. In other words, we have not been given theta 1 and theta 2. Theta 1 is actually this angle, and theta 2 is that angle. So before we proceed, we need to actually determine what theta 1 and theta 2 are. So clearly, I hope you can see that theta 1 is going to be 90 minus 30, which gives us 60 degrees there. And theta 2 is going to be the 90 minus the 54, which will give us 36 degrees there. So that's our theta sorted. Well, we can now apply Snell's law. N2 over N1 is sine theta 1 over sine theta 2. N1 for air, of course, can be taken as 1. So that leaves us with N2 equals the sine of theta 1, which is the sine of 60. Make sure you get the angles the right way round. And then sine of theta 2 is the sine of 36. And when you work that out, you'll get a refractive index of 1.47 in this case. Notice there is no unit for refractive index. It's an index. It's basically a ratio, as you can see, so it doesn't have any unit. And all refractive indices lie within a range of 1. Technically, the refractive index of a vacuum is exactly 1. And you'll find that the maximum refractive index you'll ever come across is for diamond, which is around about 2.4. You just won't get any refractive indices bigger than that. Now, you may have noticed that in the Snell's law equation, frequency is not mentioned, the frequency of the light. It doesn't appear in the equation, and that's because frequency remains constant upon refraction. So the color of light is unaffected by refraction. So if blue light goes into a block, the light will still be blue inside the block, and it will still be blue when it comes out of the block. So the actual frequency, which is what determines colour, is constant. It's not actually wavelength that determines colour, although we often talk about it as if it does. But very often you can use wavelength as a proxy for colour, but technically it's actually the frequency that changes. We go back to the wave equation, V is f lambda, as you know. If frequency remains constant upon refraction, then you can see that if the wavelength goes down in the glass, then the speed goes down as well. And that's consistent with our speed being 3 times 10 to the 8 in the air, but the speed going down to 2 times 10 to the 8 in the glass, alongside the wavelengths going down as well. So, one final thing here. If you think about it, and let's just go straight to the the wavelength version. You can see that the refractive index is going to depend on the change in the wavelength. So different wavelengths will have different refractive indices, basically. So when you change the wavelength of the light, which in practice basically means changing the colour of the light, that's the frequency, then different colours will refract by different amounts. So different colours, i.e. frequencies, of light refract by different amounts. So for a given glass, N for red is different from N violet. So just be on the lookout for that. Strictly, you can only apply Snell's law to specific frequencies of light because the refractive index for the same glass is different for red than it is for violet. You can see that actually if you think back to your dispersion experiment from previous years, where if you put in white light, like so, the red light might be refracted by that amount, but the violet light will be refracted by a greater amount, like so. And what that tells us is that N for the violet here is greater than the N for red for this glass. So in doing Snell's law calculations, you may very well have to do separate Snell's law calculations for each colour of light involved. Finally, applications of refraction. Well, the most familiar one, of course, is lenses. Lenses are used in glasses, in cameras, video cameras, still photograph cameras, contact lenses. We use these all the time. They're also used, or at least refraction is a key feature of gemstones and diamonds. Diamond has the highest refractive index of any known substance, about 2.4, and it causes a lot of refraction when light hits it. And if you cut the stone so that you've got all sorts of interesting angles for the light to hit, it then gets refracted at all sorts of interesting angles, and the colours refract by different amounts, and it glows and sparkles as a result. So that brings us to the end of this part 1 of 2.6 refraction.